thank the host for inviting me, and today I'm going to talk about machine learning, learning humans. Basically, what I'm going to do is to share with you some lessons that I myself at least have learned from the past 5 years or so of doing machine learning in material science, okay? Now, I know this is a catalysis section, but I don't do catalysis, unfortunately. So there will be no catalysis examples in the talk. However, I do believe that a lot of the lessons that we have learned will be applicable to machine learning in the catalysis domain as well, okay? Now, let me first start by something that all of us know, right? So whenever we talk about computational material science, we are really talking about the in silico design of materials from atoms to properties, right? And this is a very generic workflow that applies regardless of what kind of field you are going to work in, right? You usually start with some arrangement of atoms, and for those of us who work on ab initio computational material science, you basically try to solve the Schrödinger equation, and from the Schrödinger equation, you can get some things like the energies and forces as well as the charge density, and from that you combine that with things like the equations of thermodynamics, kinetics, and other phenomenological equations like mechanics to basically get the properties that you are interested in for the application that you want to design for, right? So I work a lot in batteries. So in batteries, we are interested in things like the phase stability of the material, the voltage of the cathode. Sometimes we are interested in the mechanical properties, and very often we are interested in the diffusion properties of the material, right? Now, the key thing here is that each of these steps involves some computational costs, right? And in this diagram, basically what I've indicated is that the smaller the arrow, essentially the more costly the step is. So typically when we talk about ab initio calculations, this step is usually the most expensive. In other words, solving the Schrödinger equation to actually get at the energy, forces, and electronic structure, okay? So this is also the reason why even today we cannot completely rely on just ab initio calculations alone to do materials design, right? So this is a chart that I'd like to show. It is basically the data history of the materials project, right? So the materials project was started around in 2011, 2012, and today we are at about 2023. And what you see is basically on the y-axis is the total number of database entries in the materials project having various properties computed, right? And what you notice is that, well, we are done reasonably well, right? So we started with, say, a few thousand structures. We've grown to about 60,000 structures or so, and recently we have gotten up to about 140,000 structures, okay? Now, however, what you notice is that in the past few years, we have essentially stagnated, right? So there really hasn't been a significant increase in the total number of materials in the materials project for quite some time, right? And the main reason is, of course, that sometimes generating ideas for new materials is difficult, and also, of course, the computations themselves are not exactly cheap, right? And the situation is even worse when we talk about other kinds of properties that we are interested in. So, for example, if you want to compute the electronic structure, in the materials project, you have about half the number of electronic structure, accurate electronic structure calculations compared to the total number of structures, right? And for things like tensorial properties, so things like your elastic constants, phonon properties, the situation is even worse. You basically have about 10% of the data that you have for things like just your basic structures and energies, right? Now, the good news is, of course, today we have a means of sort of shortcutting this process, right? We have sufficient data to basically start to do machine learning, and the general idea is to machine learn from the data that you already have and try to predict everything, all the kind of hypothetical chemical spaces or structures that you are interested in exploring, right? Just to give you an example, so for example, if you just take a very simple perovskite and you do combinatorial insertion of atoms, you allow yourself 10 A species and 10 different B species, we are already looking at the order of about 10 to the power of 7 crystal structures, right? And that's, of course, I didn't take into account symmetry here, but that gives you an idea of really how little of that material space we have already explored with ab initio calculations, and why we actually need machine learning to really explore the rest of the space, okay? So now, the general idea here is, of course, now we have all these steps. Which of these steps can we replace with machine learning algorithms, right? So one of the simplest things you can do is to replace just this very basic step. This is basically where machine learning functionals come into play. So there's been a lot of work on this front, especially from people like DeepMind in collaboration with John Perdue, where they basically develop new DFT functionals, which addresses some of the limitations of current DFT functionals in terms of things like band gaps, and you basically have better functionals for your DFT. Now, while this step is of course critically important, this step actually doesn't solve our computational cost problem, right? Because the machine learning functionals are about as expensive as your other DFT functionals like PPE, okay? Now, the other way to replace physics with machine learning is to really go from the starting process to the ending process, right? So instead of solving my Schrödinger equation and trying to do all these things in between, I basically hop from the arrangement of atoms all the way to properties, right? So in other words, I build a machine learning black box that predicts a property that I'm interested in, say, for example, the band gap or formation energy, directly from the arrangement of atoms and the chemistry, okay? Now, I will say about 80 to 90% of the work in the literature is based on this kind of machine learning models, okay? And in some instances, that is actually the only way to do it. But I'm going to try to persuade you from this talk that in many cases, that's not the way you should be applying machine learning, okay? So let me start with lesson 1, right? And one of the first lessons I learned was basically that representation is everything in machine learning, okay? And when you want to represent materials, there are really a few ways you can go about it. You can start from the composition alone, and you essentially describe your composition in terms of things like the average electronegativity of the atoms, the average number of electrons, and that's various atomic features that you can get without actually having to do electronic structure calculations, okay? Now, unfortunately, this is typically not enough, right? Because composition doesn't tell you everything, right? We know of polymorphs with very, very different energies, and if you just have a composition-based approach, you can't actually predict different energies for different polymorphs, right? So this is why, in my group especially, we focus primarily on representations that include the structure, right? So in other words, the position of the atoms relative to each other, for example, right? And there have been various structural descriptors that have been developed over the years. There are things that are based on graphs, and there are also things that are based on local environments around each atom, okay? And both have been extremely successful in machine learning models for property predictions, okay? Now, the type of architecture that my group works on primarily is graph neural networks, and it turns out that graphs are a very good universal representation for materials. You can think of nodes, the atoms as nodes in the graph, and the bonds of the atoms as basically the edges in the graph. And so what we did was to basically develop this architecture called the materials graph network, which is based on the graph network architecture that was actually developed by DeepMind. So this representation is a very generic representation that works across molecules, crystals, and everything in between. Now, one unique feature I want to point out about the materials graph network architecture, or MEGNet, is that we have this global state that allows us to represent properties that are represent a state property of the material as a whole, okay? So in most of the graph neural network architectures that you see out there, they don't actually have this state variable. And what I'm going to show you is how powerful this state variable can be, okay? You actually it actually allows you to do a lot of things with graph neural networks that you would not be able to otherwise do with just simple representations of nodes and edges, okay? Now, in any graph neural network architecture, you essentially just do graph convolutional layers or message passing. You basically pass information from atoms to bonds, bonds to atoms, bonds to global state. So other people have already talked about it. I'm not going to talk about it further, right? Now, just to show you how good graph neural network models are, so this is various property prediction models that we have developed using the MEGNet architecture and data from the materials project, right? So today, we can actually already predict the formation energy of any crystal structure to within about 28 to 30 MeV per atom or so, okay? So this is, of course, a number based on the MEGNet architecture, but I would basically admit that a lot of the other graph neural network architectures would give you roughly the same result, okay? So 30 MeV per atom seems to be a good number that almost all the architectures give you. We can get things like the band gap to within about 0.33 eV. You can also predict things like the Boutin-Scher models, right? Now, is this 28 MeV per atom accuracy good enough, right? And it turns out that it's actually quite reasonable, right? So this is actually an analysis that was done by Wenhao Sun back in 2016, where he essentially looked at the energy above the ground state for all the crystals in the ICSD, right? And crystals in the ICSD, most of them have already been experimentally realized, right? So what he found was that about 80 to 90% of the crystals in the ICSD, they fall within this threshold of about 100 MeV per atom above the ground state, right? What this means is that even with an accuracy of about 28 MeV per atom or so in the formation energy, we can already make a fairly good assessment, or with some reasonable confidence, whether a crystal is likely to be stable and synthesizable or not, right? So it's not 100%, but at the very least, we can exclude very high energy structures, like things which are 1 eV above the Hall or a few hundred MeV above the Hall, right? So, so this is actually promising, right? Okay. Now, the second lesson that I actually learned from doing machine learning and material science very early on was that it turns out that these graph neural networks models actually learn chemistry, right? And how do they learn chemistry, right? So we actually took the elemental embeddings that were learned by the model during when we fitted the formation energy models. And what we did was to basically plot the correlations between the elemental embeddings of all the elements. And we also did a TSME plot, right? And what we found was that essentially, if you look at this plot, which is arranged by Mendeleev number, is that the correlations between the elemental embeddings actually reproduce the periodic table, right? You can see that, for example, things like your alkaline metals, they all have very high correlations with one another. In other words, they are very chemical similar, right? And even for something like europium, right? Europium, typically people think of it as a rare earth metal, but you will see that europium actually has very high correlations with all your 2+ ions, right? Like calcium, barium, strontium. And this is, again, very consistent with what has been experimentally found, right? Your europium 2+ can actually substitute for a lot of these compounds, especially if you are working in phosphor materials like me. Europium 2+ is actually a typical dopant that you actually put into barium-containing compounds or strontium-containing compounds to actually make a phosphor, right? So, in other words, what I want to stress here is that it is not true that the models are just complete black boxes, right? If you take a look closer at what the models are actually learning, you actually find that they have learned very useful chemistry, right? And of course, this is also reinforced by the TSME plot. You can see that, for example, all the rare earth metals are clustered here. You have all your alkaline metals here. So in other words, there is a certain relationship between the distance between atoms and the chemical similarity of the elements, okay? All right, so this learned chemistry is actually very useful. You can actually use it to address certain data limitations. So there's this framework that we developed called the atom sets framework, which just all that we did was to basically extract out, essentially what we're doing is that we use a pre-trained graph neural network model like MEGNet as an encoder, right? And what we did was to basically just extract out the intermediate layers of the graph convolutional layers. So we extract out the elemental features as well as the finer features from the graph convolutional layer features. And we just simply use a feed-forward neural network or multi-layer perceptron to basically try to predict different properties, right? And what we found was that basically in doing so, you can actually build models for very small data, right? So the previous speaker have already talked about pre-trained models, right? So here what we are doing is that we use a pre-trained model as an encoder for structures, and we find that that encoding is actually a very efficient representation for predicting different material properties, and even when the data set is extremely small, okay? Now, another way in which we can address the data problem is through multi-fidelity models, right? So it is a truism that we all know in material science that basically high quality data is expensive to get, right? If you want to get an accurate band gap, you can do a HSC calculation, which is several orders of magnitude more expensive than your standard PBE calculations. You can also do it experimentally, which is even more expensive, right? And so it is of course not a surprise that we have a very large data set for PBE data. So if you just go to the materials project, you can get about 52,000 band gaps. But if you are trying to get a HSC band gaps, you have about one order of magnitude smaller data set, and of course you have even fewer experimental data, right? And this is where that global state variable that I talked about just comes into play, right? It turns out that we can use this global state variable to encode information about the fidelity of the data that we are using. So we can use one encoding for PBE, one encoding for HSE, and one encoding for experiments. And what this allows us to do is that instead of training one model each for PBE data, HSE data, and experimental data, in other words, we are training, for example, the experimental data with a very small data set. We can instead train one single model that uses all available data with all fidelities, okay? So in other words, we can take all this data that we have, including the less accurate PBE data, and we throw it into a single model that can predict band gaps for any fidelity, right? And this actually turns out to work remarkably well, right? So if we just train a model for each of the fidelities in turn, what you notice is that, for example, with PBE, we can get mean absolute error in the band gap of about 0.3 EV or so, but your errors on your HSE and experimental data is much larger, right? If we actually combine fidelities, let's say PBE plus one high fidelity data, or sometimes we can just take PBE plus all the high fidelity data, what you notice is that immediately the mean absolute error in the prediction of HSE band gaps and experimental band gaps then decreases to about the same level as your PBE band gap, okay? So in other words, we have managed to address the small data problem for things like experimental band gaps and HSE band gaps without actually having to generate any more HSE data or experimental data, okay? So in essence, we are getting something free for nothing, right? So, and it's very rare in material science that you actually get that, okay? So this just shows you that sometimes just by subtle differences in the architecture and applying them in a different way, you can actually address some of the issues that we have that are unique to material science, right? Which is essentially that your data sizes usually tend to be quite small, okay? All right. Now, this is where lesson 3 comes in, which is keeping as much of the science as possible, right? So if you recall, we just now talked about the structure to property prediction, right? In other words, I just give you a structure, I ask the machine learning model to tell me the property, right? There are a few limitations, okay? So number one, you actually require an input structure, right? And most of the time, you actually get an input structure from DFT calculations, right? And that's not ideal, right? We want to, if possible, skip DFT, right? There are also some properties that are emergent or do not have a continuous relationship with structure and composition, right? Now, The reason why so many people are interested in things like neural networks is basically because of this theorem called the universal approximation theorem, right? And the universal approximation theorem basically states that a neural network with one hidden layer can approximate any continuous function for inputs within a specified range, okay? Now, so people were naturally very excited, right? Well, we can represent any function, it should work for everything, right? What they forgot was basically it says continuous here, right? So, and continuous turns out to be quite important because in material science, we frequently encounter discontinuous properties, okay? I can give you an example here, right? So this is the field that I worked in, basically solid state electrolytes for lithium-ion batteries. And this is basically a plot of the conductivity versus aluminum content and the different phases for this garnet solid electrolyte called LCO, right? And what you notice is that you just have 2 orders of magnitude change in the ionic conductivity of the garnet just from slight changes in the doping content of aluminum. Very, very small changes in the doping content. You also have a very sharp change when your phase change from a cubic phase to a tetragonal phase. And that change from cubic to tetragonal, again, is a very, very subtle difference in lattice parameters, okay? They still look almost cubic, okay? So, in other words, this is the very example of a discontinuous change, right? That you, just from very tiny changes in concentration, you already have a very large change in the property. And machine learning models are actually terrible for predicting this kind of effect, okay? So what's the solution, right? So this is where my proposal comes in, right? Which is that for a lot of the properties that we are interested in, there is actually no need to go straight from structure to properties. You can actually do structure to just energy and forces. In other words, the potential energy surface. And then if you are able to predict the energies and forces, you can already apply a lot of the thermodynamic equations and kinetic equations to derive the property that you are interested in. Okay, so once you have the potential energy surface, you can run MD simulations to get ionic conductivity. You can run equation of state curves to get your bulk modulus and so on and so forth. Okay, so machine learning interleaved potentials are of course one of the big success stories of machine learning in material science. Okay, there are many formalisms that have been developed over the years. I'm not going to go through all of them. But by and large, the way they work is to basically take the local environment around each atom to describe it in terms of some local environment fingerprint, and then you use a machine learning model to basically relate your energy and force to that local environment fingerprint, okay? And there's been various types of machine learning models that have been applied. Again, I'm not going to go into the details of all of them, but just to summarize, the reason why they are so successful so far is that they are rigorous, they are automatable, and they are high performing, right? So if you compare, say, your machine learning interleaved potentials with your traditional interleaved potentials, invariably you can always get a much more accurate machine learning interleaved potentials in terms of energy accuracy and force accuracy compared to your traditional interleaved potentials such as EM and mean, right? But what is even more important is that the fitting of machine learning interleaved potentials is largely automatable, right? So today, if you ask one of my students to actually fit a machine learning interleaved potential, they can probably get you a good potential within a week or 2, right? And that used to be not the case, right? It used to be that fitting one interleaved potential for any system of interest takes an entire PhD, right? So this is really the transformative effect of this approach that has been on the material science field, right? Just to show you some examples, people have used, for example, my group have used machine learning interleaved potentials to study things like solid electrolytes for lithium-ion batteries, and what we find is that we can we can investigate a lot of physics that we were not able to do before, because we can actually simulate all the way down to room temperature rather than having to rely on high temperature simulations. We also apply machine learning interleaved potentials for things like high entropy alloys or multi-principal element alloys, and we can study things like this 1 million atom system where we actually have a polycrystalline material and look at the phase segregation. Okay. All right. So the problems with all the traditional machine learning potentials, however, is that their number of terms grow combinatorially with the number of elements, and they do have to be custom fitted to each chemistry of interest. So what this means is that they cannot really be used for broad-based materials discovery, right? So this led us to think, well, can we actually apply graph neural networks to build inter-domain potentials that are scalable to the total number of elements, right? And this is where we develop what we call the materials tree-body graph networks. In other words, we take inspiration from our traditional inter-domain potentials, such as your bond order potentials or tensor potentials. We include tree-body terms into our graph neural network architecture, and then using this architecture, we are going to fit inter-domain potential that is for the entire periodic table of the elements, okay? So to do that, we actually use one of the least used data in the materials project. So Andrew has talked about identifying materials project data that people have not looked at carefully, okay? So it turns out that we have done about 100,000 DFT structure relaxations since 2012. That gives us about 100,000 energies, about 10 million forces, and about 1 million stresses. And all that data covers about 89 elements of the periodic table, right? So what we did was very simple. We took all that data, we threw it into that M3GNet architecture and tried to fit an inter-domain potential that works across the entire periodic table, right? And I call this basically an AlphaFold for material science, right? AlphaFold being used to predict protein structures, but now we have an inter-domain potential that can be used to predict structure for any arrangement of atoms in a material, okay? So what this enables us to do now is that we can now do DFT-free structure relaxations, okay? So we can show that using M3GNet, the M3GNet universe potential, we can actually predict the volumes of crystals to within about 1 to 2% of the DFT relaxed crystal structure, okay? So in other words, we can already get accurate crystal structures without having to do any DFT calculations, right? And the energy error, in other words, the error of the above the ground state, it turns out to be still about 30 to 50 MeV per atom or so. And with this accuracy, we can already make stability predictions for any hypothetical crystal structure without having to do DFT, right? And those stability predictions are actually quite good, right? So this is actually a distribution graph of some hypothetical compounds that we generated, and you can see that the distribution of the E above Hall between M3GNet and DFT is actually quite similar, okay? We can, and of course the inter-domain potential has applications other than just calculating energies and relaxing crystal structures, right? We can now dynamically simulate a lot of properties that would otherwise be very expensive to do in ab initio calculations. We can calculate the phonon dot center. You can see that the agreement again between DFT and the M3GNet potential is pretty good. We can calculate the bulk modulus. We can even do MD simulations to get the ionic conductivity. And here I show you an example of one lithium superionic conductor, and you can see that again the agreement between M3GNet simulate the ionic conductivity and the AIMD conductivity is actually again pretty good. Okay, so all this is implemented in this public GitHub repo called MatGL, or Materials Graph Library, okay? So it is a collaboration with Intel, and it has multi-GPU support. So if you are interested in trying out M3GNet for yourself, you just go to matgl.ai and you can actually download the code, okay? Now, since the publication of our work, there have been quite a bit of interest from the community. So I myself am the developer of PyMatGen, so I actually integrated M3GNet into PyMatGen itself. So what this means is that today you can generate some hypothetical crystal structure. You can use M3GNet to relax it. And if you feel like it, you can do a DFT calculation afterwards. And your DFT calculation will actually go a lot faster, okay? So we have actually shown that consistently across many systems, okay? There have also been commercial developers such as the Amsterdam Modeling Suite who have integrated M3GNet into their software, and we have one company even helping us develop a LAMMPS interface for M3GNet, okay? All right, just to show you, we have been using MTGNet to search for lithium superionic conductors for all solid-state batteries. These are all the properties that you are interested in for lithium superionic conductor. So things like the phase stability, the electrochemical stability, ionic conductivity, electronic conductivity, and mechanical properties, right? And what you notice immediately is that out of all these properties, almost all of them, you can get it from just the potential energy surface, right? You don't actually need direct material to property prediction. So phase stability and electrochemical stability, you just need the energies. Ionic conductivity, you can run MD. Electronic conductivity, which you require to calculate the band gap, that is the only thing that you can't get from just the potential energy surface alone, okay? So that you actually need to use a material to property model. And bound and show modulus, as I shown, you can actually just do a dynamic simulation of the material, okay? So we are conducting what we call a massive scale search for lithium superionic conductors. We are up to about 31 million different crystal structures already, 1.8 million which are predicted to be potentially stable. Here I show you essentially the predicted electrochemical windows with MPGNet versus, say, a PPE calculation for a well-known lithium superionic conductor. And what you see is that you basically can't tell a difference between them, right? Essentially, you can already predict the electrochemical stability without having to do DFT. This is basically a plot of the mean square displacement at 1200K versus the mean square displacement at 800K. You notice that all the well-known lithium superionic conductors sit in this region over here. This is the good lithium ion conductor region. Basically, materials with a fairly high diffusivity at low temperatures and a fairly low activation barrier for diffusion. And we are, of course, exploring all these gray dots in this region, which have not been explored for lithium superionic conductor applications, okay? All right. You can also improve MPGNet further by intelligent sampling. What we have done is to develop this, what we call a direct sampling approach, which utilizes dimensionality reduction, clustering, and stratified sampling to basically ensure that we actually cover all the configuration space that we are interested in. And the result is basically a much more accurate MPGNet that extrapolates far better to unseen chemistries, okay? So this is something that we just recently published a few weeks ago, okay? All right, I'm going to conclude. Basically, hopefully through this talk, I've convinced you that replacing ab initio calculations with machine learning should be done with care and domain knowledge. My rule of thumb is basically I want to replace the smallest possible step with machine learning, and I want to retain as much of the science as possible. So I have a bias for machine learning intelligent potentials and not material to property prediction models, okay? Graph neural network models, especially things like MPGNet, they are really, I believe they are really like the foundation models for material science. In other words, starting from an MPGNet model, which has already been trained on 89 elements of the periodic table, you can today now create custom potentials much more quickly than if you start from scratch and with less data, okay? So definitely do try it out, right? And finally, I want to stress that the primary challenge in material science is really not ML architecture. I mean, I know that there are new architectures being come out with every day, and by and large, you will see that they are not too different, except in some minor details, and their performance usually is not too different either, right? And the problem that we are facing is really data, right? The quantity of data, the heterogeneity of data, and the diversity of data. And this is where I believe approaches such as multi-fidelity approaches, as well as intelligent sampling approaches, will actually help us overcome some of these challenges much more quickly, okay? I just want to acknowledge my group for the work, especially Dr. Chichen, who developed a lot of the graph neural network work. Funding comes from the materials project under the Department of Energy, and I am happy to take any questions. Thank you.